Hello, my name is Gabriel, and today I'm gonna work on Lab 3 circuits. The purpose of this lab was to examine circuits containing resistors in series and in parallel, also examine ohmic resistors and capacitors, and measure potential difference in conventional current within the circuits. The fundamental equations and principles used were Ohm's law. The equations are displayed, loop rule, junction rule, and capacitance. The results for this lab was that the time constant obtained was 6.17 seconds. The system for this lab were the circuits, and the surroundings were considered to be anything else, Earth. For experiment 1, the circuit is displayed on the right. The predicted current was of 0.02 amps, and this was done by using Ohm's law with measuring voltage and resistance, total resistance of the resistors in series. And the experimental current obtained was the same as the predicted one. When the connection of the ammeter was reversed, the readout remained unchanged. For experiment 1, I also measured the voltage across different points in the circuit, as shown on the right. The values are displayed on the left, and the experimental data was in agreement with the loop rule, as in the changing voltage of the loop would be 0, and that's the values obtained. From AB, it's 3 volts, subtracted by CD, negative 0.96, and EF, negative 2.04, and that yields 0 volts. This is a plot showing the changing current over time, and it basically reflects the data shown in the previous slide. And questions asked were, when inserting a voltmeter, it did not affect any of the ammeter measurements because negligible current flows through the voltmeter, which doesn't really affect ammeter measurements. Also, connecting the ammeters with the 100 ohm resistor actually increased the current because now the current flows through the path of least resistance, which is the ammeter itself, instead of the 100 volts, 100 ohms resistor. For experiment 2, we had an RC circuit as shown on the left. There were two 1.5 volt batteries, one Faraday capacitor, and two light bulbs of different resistance. We connected the light bulb in the current resistors area. For the experimental calculations, we calculated the time to discharge the bulbs and also to charge the capacitors. The data obtained is shown. Then a plot of ln of voltage over initial voltage versus time is shown. And the RC constant is calculated by fitting the data to a trend line and calculating the negative inverse of the slope. And that yielded 6.17 seconds. The expected time in ideal calculations will be 6 seconds. And because our value is very close to 6 seconds, we can say that the experiment is reasonable. For the final discussion, we asked, what if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this happen in real life? So basically, the capacitor would reach full charge instantly, according to this equation. If you plug RC very close to 0, the value goes to infinity, and then delta V is equal to delta P0. And this will not happen in real life because anything we use have small resistance, as in the wires and any other instruments used for measurements. And also, we need to account that this will not happen because, according to Ohm's law, if R goes to 0, then that means that the current would go to infinity, which is also not possible in real life. Some sources of error for this experiment were that the equipment was very old and some of it was malfunctioning. We had to switch ammeters and voltmeters a lot. The emitters had low precision and only went to one significant figure, and there were no consideration for no idealities.